Welcome to this module on deflection methods. My name is Martin Sanderson and I'll be taking you through the key concepts. This module will be broken up into 3 sub-modules for ease of learning. In directional drilling, one of the most important challenges is to deliberately alter the well path in a controlled way. We call these processes deflection methods. They allow us to take off from a vertical position, adjust the inclination, change the azimuth, or sidetrack around an obstruction. Over the years, several methods have been developed, each suited to different lithologies, well designs, and operational contexts. Some are mechanical, relying on whipstocks or bent housings, while others are hydraulic or electronic, such as jetting or modern rotary steerable systems. The aim of this module is not only to list these methods, but to understand how they work, where they are best applied, and what their limitations are. Directional drilling is as much about control as it is about deviation. At the end of this module, you should be able to demonstrate 3 things. First, you'll be able to list the 4 main deflection methods used in directional drilling: whipstock, jetting, steerable positive displacement motors, and rotary steerable systems. Second, you'll learn how controlled deflection is actually achieved in each case. That means understanding not just the tool components, but the mechanisms, whether it's the face of a whipstock guiding the bit, the hydraulic power of a jet spudding a pocket, the bent housing of a motor creating curvature, or the electronic control of a rotary steerable tool adjusting trajectory while rotating. Finally, you'll examine the advantages and limitations of each approach. No method is universal. Formation hardness, well complexity, cost, and operational risk all influence the right choice. By articulating these trade-offs, you'll be able to explain why a whipstock might be selected offshore for casing exits, why jetting is confined to soft formations, or why rotary steerable dominates in extended reach wells. These objectives provide a clear framework: know the methods, know how they work, and know when they are best applied. With that roadmap, let's now explore how we can deflect a well path in practice. From these early beginnings, the industry formalized 4 main deflection methods: whipstock, jetting, steerable motors, and rotary steerable systems. The choice among them depends heavily on lithology. The harder the formation, the less suitable jetting becomes, while in softer zones, jetting can still be effective. Understanding this evolution helps us appreciate why we now rely on sophisticated steerable technologies. So question: if want to sidetrack from inside casing, what would be my tool of choice? I will give you a moment to think. The clue is that we are having to sidetrack through casing. Today, the majority of the applications for whipstocks are to sidetrack old wells to reach unswept reserves. Setting a whipstock, then using a milling assembly to mill through the casing and create a rat hole so that a drilling BHA can then be used. Typically, the drilling assembly would be a steerable motor or a rotary steerable, which would continue to steer to the end of the build-up section. The Gilligan assembly is a flexible, rotary build-up, bottom hole assembly designed to create controlled curvature without a motor. The key is a highly flexible component, typically heavyweight drill pipe or a slim drill collar, placed above the near bit stabilizer. By exploiting this flex, the assembly can achieve high dogleg severities, often greater than 10 degrees per 100 feet, depending on tubular stiffness and stabilizer spacing. Control comes primarily from weight on bit. Increasing weight on bit amplifies the natural tendency to build, backing off weight on bit tempers it. A roller cone bit is recommended for durability and tolerance to intermittent lateral loading during the build. Operationally, you must survey inclination very frequently, about every 5 feet, to track the actual build-up rate, BUR, and avoid overshooting. Because the method offers little to no azimuth control, simple topco or underdrift single-shot tools are adequate. This is fundamentally a blind sidetrack technique. Historically, the Gilligan was widely used before motors became commonplace and remains a useful fallback in hostile formations when motors or steerable systems struggle. The whipstock was the original open-hole deflection tool, used long before steerable motors became standard. Its main advantage was azimuthal control in formations that could not be jetted. However, early whipstocks were far from reliable. Problems included the whipstock turning in the hole while drilling off the face. Operationally, whipstocks were cumbersome. At a minimum, they required 3 trips: one to set and orient the whipstock, one to drill the pilot with a hole opener, and another to run a rotary assembly from about 3 degrees of inclination. If cementing was required, add another trip. Orientation itself required multiple free gyro or single-shot surveys with a UBHO sub. These inefficiencies meant whipstocks were quickly abandoned once steerable motors became available. Yet, they represent an important milestone in the history of deflection, our first real attempt to control both inclination and azimuth in open-hole conditions. Understanding their limitations helps explain why later technologies evolved and why whipstocks, although largely obsolete in open-hole, found new life in cased-hole applications. The picture on the right provides a rule of thumb for selecting the appropriate deflection method. The numbers refer to IADC roller cone bit classification. In very soft formations, a jetting bit should be used. This is because the formation is so soft that it washes away in front of you, which prevents other defection mechanisms from operating correctly. Once we have competency of the formation, steerable motors or rotary steerable tools are ideal. Often, when we are kicking off, there is a cement plug in place, and the bottom hole assembly is using this to kick off from. The cement has to be harder than the formation, otherwise the steerable assembly will take the weakest path. Therefore, when the formation becomes really hard, a whipstock has to be used. When the formation becomes very hard in the region of 30,000 psi and greater, normal bits are not strong enough to drill, and we need to move to impregnated diamond bits. These bits drill by grinding on the formation, which is a very slow process, so we run them with turbo drill motors. These are high RPM, low torque motors, often spinning the bit well in excess of 1000 RPM. Whipstocks were once the primary open-hole deflection tool before the development of steerable motors. They were valued because they allowed azimuthal control in formations too hard for jetting. However, early whipstocks suffered reliability problems. The tool often rotated while drilling off the face, making orientation inaccurate. Fill or cave-ins could block the rat hole during trips, and hole opener sag or collar wear on the high side reduced the actual inclination achieved. These issues made whipstocks cumbersome and inefficient. Typically, 3 trips were required, one to set and orient the whipstock, one to drill with a hole opener, and one to run a rotary assembly to continue drilling. A 4th trip was often needed if cementing the whipstock in place was required. Each orientation demanded multiple gyro or single-shot surveys with a UBHO. Because of these operational inefficiencies, whipstocks quickly disappeared with the introduction of steerable motors, which offered greater reliability and required fewer trips. Still, whipstocks were a critical early solution in the evolution of directional drilling. They taught us that precise deflection was possible, even if imperfect, and set the stage for later innovations. Understanding their limitations helps highlight why motors and RSS technologies became the dominant methods. Today, whipstocks have made a comeback. One-trip systems enable us to hang the whipstock on the bottom of the drilling assembly. This enables us to set the whipstock in place and drill out in one go. In mature fields where old wells are being repurposed to target unswept reserves, this is very beneficial. As mentioned on the previous slide, open-hole whipstocks fell out of favour with the arrival of steerable motors. They experienced a renaissance in cased-hole applications. Offshore, where operators needed to sidetrack from inside casing, whipstocks offered a precise and efficient method. Previously, operators milled a section of casing, set a cement plug, and then attempted to sidetrack with a motor, a process full of uncertainty in both exit depth and azimuth. The introduction of cased-hole whipstocks changed that. With gyro guidance systems, whipstocks could be precisely oriented, generating predictable exits and reducing uncertainty. They also created manageable quantities of swarf and cut sidetrack times significantly. In deep water, where daily operating costs could reach $1 million, modern open-hole whipstocks with hydraulically activated anchors save days by eliminating cementing and waiting on cement. Although these systems required specialized tools and personnel, the cost was easily offset by the time savings. That said, open-hole whipstocks tend to have limited use onshore due to cost. Today, they are primarily used offshore for controlled casing exits and sidetracks, proving that an older technology can still have significant value when applied in the right context. Before we move on to the next slide, I have a question. How do we orient the whipstock inside the casing so that the whip face is pointing in the right direction? I will give you a moment to think about this. Well, the answer depends on the inclination of the hole. Ideally, the inclination is above 7 degrees. At this point, we can use the inclination readings on the MWD tool. This is given in the form of a continuous tool face reading to a monitor on the rig floor. The directional driller will then orient the whip face to point in the direction of the kickoff point. If the inclination is below 7 degrees, the MWD relies on magnetics, which are of no use in casing. Therefore, a gyro will be needed instead. This tends to be more time-consuming. This video demonstrates the operation of a cased hole whipstock. The video started at the top of the BHA. The first component highlighted is a bypass valve. This allows circulation while tripping in and setting the whipstock. Next is the heavy weight, which is used as a flex joint to provide mass and enable some flexibility. The running tool has hydraulic fluid, which is used to set the anchor. Next, we are at the mill assembly. At the bottom is the lead mill, which will mill the casing for the sidetrack. Behind this is the following mill, which cuts the top of the window in the casing above the whipstock slide. Both the lead and the window are under gauge. Above this is the string mill. This is normally full gauge and dresses off the window for a smooth finish. The mill is attached to the whipstock by a shear bolt. From the nozzle of the mill, a hose carries hydraulic fluid from the running tool to the anchor at the bottom of the assembly. Before setting the whipstock, it needs to be oriented so that the BHA kicks off in the right direction. Once this is done, the anchor can be set. This is normally achieved by increasing the flow rate until the bypass is triggered, which directs pressure to the running tool. Hydraulic fluid pressures up in the anchor and the dogs are extended out to lock against the formation. When the hydraulic anchor is locked in place, the BHA is moved up and down to shear the bolt holding the assembly to the whipstock. When the bolt is sheared, the BHA is pulled up above the whip face and a low RPM is applied. The BHA is then lowered onto the whip face and the sidetrack is initiated. As the mill travels down the whip face, it approaches the halfway point and the milling efficiency drops significantly. At this point on the whip, there is a mid-ramp to push the mill past the midpoint and into the formation. When the mill is fully embedded in the new formation, the assembly is pulled back through the casing several times to dress it off. The drilling then continues until a reasonable rat hole is achieved. Let's revisit the learning objectives to consolidate what we've covered. First, you should now be able to list the four main deflection methods: whipstock, jetting, steerable motors or turbo drills, and rotary steerable systems. Second, you should understand how each achieves controlled deflection, whether by mechanical wedge, hydraulic jetting, bent housing motors, or electronic pad and mandrel systems. Third, you should be able to state the advantages and limitations of each. Whipstocks are reliable in casing exits, but less efficient in open holes. We will continue with whipstocks in the next section before moving on to steerable motors and rotary steerable tools. Thank you for watching this presentation on deflections. Please progress to the quiz.